What I'm going to talk to you about today are actually two stories. I'm going to tell you two stories. One is the human story of how we humans stumbled upon the radiation, the background radiation that was instrumental in unraveling and revealing to us the story of our origin. But I'm also going to tell you a little bit about the cosmic story of how that radiation arrived on Earth so that we could detect it and unravel the story that was hidden inside it. But now let me tell you that these two stories are the same story. Because what was started by the cosmos 14 billion years ago is what has created the possibility within us humans to have the sensitivity and the wherewithal to be able to understand the message that the cosmos had been giving us for millions and even billions of years. So our being able to unravel this story is simply the most recent chapter in the story of the cosmos. So it's really a single story, right? So before I get into that, I want to acknowledge this building and the land that we are on right now. Karen did an amazing job on the top of Crawford Hill to orient us to what's around us here. What I want to do is to tell you a little bit about this building and some things that happened here that you may or may not be aware of. So here's an aerial view of the building that we are sitting in right now, which is now called Bell Works. And for the longest time, it was one of the major headquarters, not the headquarters, but one of the major buildings that housed the researchers in Bell Labs, which was a part of AT&T. So I want to tell you a few personal things about this, and then I'll tell you more about the science behind it. Well, one personal thing is that I personally worked in this building for 15 years. Just a couple of stories up was where my office was. So I have a connection with this building for sure. The second personal thing I just want to tell you is that my younger daughter is going to get married in this building in a couple of months. And that makes it very personal. And in fact, me and my wife who's sitting here, both of us have been frequenting this building almost every week, talking to the event planners and the coordinators and all of that stuff. But it's been very exciting, and we're looking forward to it. Well, now let me tell you a little bit about what else happened in this particular land. So even beyond the connection to the horn antenna, which I'll tell you a little bit more about, this piece of land was bought by AT&T Bell Labs in the 1920s. This is when there was not much of anything here. This was a farmland, basically. The Garden State Parkway, which is the main thoroughfare here, was not even there at that time. AT&T was headquartered, and Bell Labs was headquartered in New York City, and they needed a place in which they could stretch out all their telecommunication wires so that they can do experiments and research work on how transmission takes place. So they looked for a flat piece of land, they found this one, and they opted to buy it. And one of the experiments that they were doing was to see the effect of thunderstorms on microwave transmission. Now, microwave transmission is a kind of transmission where you don't have to lay wires underground, so it's much cheaper, and you can simply send microwaves from one place to the other, and by doing that, you can essentially do long-distance communication. So they hired a guy called Carl Jansky, and they told him, please figure out how we can improve this interference that we keep getting from thunderstorms. And he set up an antenna On these grounds, in fact, we know pretty much exactly where that place is, and there's a monument to him right now. If you want to go outside, you can actually check it out. And while he was looking at that, he found a static, a hiss, not unlike the hiss that was discovered in the horn antenna. And this particular hiss had a daily a period that it would peak at a certain time, and then it would go down again and peak at a certain time. Well, to take a long story short, he finally figured out that that hiss of radio waves was not coming from any thunderstorm, it was coming from the center of our galaxy. That is the beginning of the science that led to the horn antenna, the science that is called radio astronomy. Now, why is this event so significant? It is because for the past many hundreds of years, the only connection that we had with the cosmos was through visible light. That's what all our telescopes are about. They capture visible light and amplify it so that we can try and make sense of what's going on in the universe. But if you know a little bit about electromagnetic radiation, which is basically what light is, you would also know that light, visible light, represents a tiny sliver of the full electromagnetic spectrum. And our eyes are only sensitive to that sliver, first of all, because sunlight is peaked in that particular spectrum, and also because we humans evolved to make sure that whatever sunlight lit up for us, we would be able to see so that we can navigate our way through the environment that we are in. So this huge other spectrum was not available to us until Carl Jansky did his experiment and realized that the universe was sending us messages not just through visible light, but through other parts of the electromagnetic spectrum. We now know that the universe has been giving us information, not just even visible light and radio waves. It is giving us information in infrared light. It's giving us information in ultraviolet light. It's giving us information in X-ray light. It's giving us information in gamma ray light. And it is giving us information in microwave light. So the universe has not spared any part of the spectrum to send messages to us humans about what our story of origin is. And I find that amazing that this is what has been going on, not just now, but for eons of time. It was just we humans that needed to wait until we could develop the sensitivity and the intellect and so forth to actually be able to decipher what the universe has been telling us. So here is the monument on the grounds of this building that honors Carl Jansky. What you see below is actually a picture of what his antenna looked like. The plaque is actually right there on the abutting road to this building. So if people are driving by, they can actually read that. In the middle is the newspaper article that appeared in 1933 in New York Times that talks about the discovery and this static and hiss. And then on the extreme right is a picture of his real antenna, which was about 100 feet tall. So this place that we are sitting in here is the birthplace of radio astronomy. And then more things happened here. As Bob Wilson explained in his talk at the Hill today, there was a desire on the part of telecommunications company all over the world, and certainly the US was not going to be left behind. The Cold War was still quite hot at that time, and so they decided that they would make satellite telecommunications happen. This balloon, which is what Bob referred to as well, it was a mylar metallized balloon, and it was our attempt to try out some kind of communication even before the satellites could be sent up into our sky around the Earth. So it was to get the transmission from such a balloon that the horn antenna was established or built. The horn antenna, as you know, is a very sensitive instrument that can block out all the noise and essentially receive this communication where other antennas would never be able to do that. And here is a picture of the horn antenna. So in 1964, Penzias and Wilson, and I don't have to tell you that story anymore, you heard it from Bob, they accidentally discovered the radiation that was coming from our very origin. Now, the point that I want to make with this is that the universe is there, and it holds for us all kinds of possibilities. The fact that there was this radiation coming from the universe is a possibility that was present for an extremely long period of time. What is so amazing is that we humans evolved the right sort of sensitivity to finally be able to detect this radiation and be able to unravel the story from where we came from. Now, you can look at that in two ways. You can look at it and say, well, that is something that had to happen. Over time we were supposed to evolve and become more smarter and things like that. But I would like to submit to you that there is another way to look at this, and that is to consider that this possibility that is there and made available by the universe is also partly responsible for drawing out the capacities and the capabilities that are needed for us to unravel the story. So this approach tells us that we as humans are set up already and are being drawn by the universe to evolve in a way that the universe has, in some sense, already anticipated for us to do. I mean, I'll tell you more about what's hidden in this radiation, but the feeling that you get when you think about this is that the universe, in a sense, knew that it was going to evolve into us humans at some point in time on some planet somewhere in the universe, and that this story that it was sending to everywhere, not just to our planet, by the way, this particular radiation gets to every single planet, every single star, every single galaxy in our whole universe. And so that anticipation, to me, is very meaningful because it gives us a new way to think about evolution that you may not have thought about in the past, because you're often told that evolution is simply a random event that happens, because random things happen and some things work and other things don't work. So I would like to give you a new way of thinking about evolution that is becoming available to us when we realize some of these things. So let me go on to this story that I wanted to tell you, and that is the human story that I talked about. And of course, it starts with Einstein. So in 1915, Einstein stumbled upon, or I would say that he worked on it. I mean, that's more than stumbling, I think. But he had actually wanted for a long time, that was, I would say, his passion, to find a new theory of gravity. He knew, he had this insight that something was not right about what Newton had discovered about gravity, and he wanted to find a new thing. And after 10 years of intensive research and work, he came across this particular theory. Now, I'll tell you a little bit about the expansion of the universe, which was discovered later on by Hubble. But what I want to tell you now is that the hints that such an expansion was there started even before we human beings had the ability to actually technologically be able to observe that expansion. And so Einstein developed his theory, and what his theory says is that space and time are not what we make them out to be. We think of them as just a stage on which the universe plays its drama, but indeed that space and time are very active agents in the story of evolution. They can warp, space and time can curve, can warp, and by doing that, it creates this sense of gravity, which, as you know, is critical to all of the evolution that is to follow from it. So this is what Einstein was extremely, delighted that he was able to come up with a better explanation for. But here's the interesting thing. I spoke about how Carl Jansky stumbled upon radio astronomy, and we all heard today about how Penzias and Wilson stumbled upon the radiation that is coming from the cosmic origins that we have. And here we see that Einstein, by using his theory of gravity, stumbles upon the possibility that this is telling us that our whole universe is expanding. So you see there is a message here as well. We humans follow our passions, our yearnings, our longings. And that's what we should be doing. But in the process of following our yearnings and longings, we stumble upon things that we would not have dreamt of. Nobody could have imagined that we would have discovered the horn antenna radiation. Nobody was prepared for it. So I personally believe that what this tells us is that if we understand what truly drives us, and I believe that everybody has their own thing that they feel their life is about, that if we follow those inclinations, that things will happen that we would be amazed and surprised by, that will lead to all sorts of breakthroughs. I mean, those breakthroughs don't have to be in terms of science. There could be breakthroughs in your own life. They could be breakthroughs that, things that you never imagined that you are possible or capable of suddenly happen. But I find this a very, very heartening and important message that we get from these stories that I'm telling you about. So now the interesting thing that some of you may have heard is that Einstein was not happy when he found out that his equations were telling him that the universe is expanding. Why was he not so happy? Because by the time that, this is hard for us to understand today because we're so used to the Big Bang theory now, we know, of course the universe is expanding. But for Einstein, he had lived through an era where this idea that there is any kind of change going on over time in the universe was unthinkable. People had established that the universe was an eternal thing that just kept the way it is, and things just keep happening for on and on. And interesting to understand, and this is very much connected with what Karen led us in, on the hill today, is that we humans need to be oriented. We want to live in a place that tells us where we belong in that place, what is our role in that place. And fortunately for us, this was the case until Copernicus came along. We believed until then that the Earth was in the center of the universe. And we were able to weave around that center stories that gave meaning to our lives. Right? When you have a shape, then you can do some things like that. But after Copernicus, we lost our centrality to the cosmos. We were simply one other planet going around the sun. And then we found out that the sun was one other star going around the galaxy around the center of the galaxy with 1 trillion other stars. And then we found out our galaxy was just a rather small galaxy in the universe, and on and on and on. There was nothing special about where we were. When this is where you are, then how do you make a story? How do you give meaning to your home? And that's exactly where things were when Einstein came to this, and his mind was so set on thinking of the universe in that way that he was completely taken aback. And he, in fact, changed his equation. He changed his equation to create a situation that would allow him to predict that the universe is not changing, it's eternal. Well, here's what the universe looked like in Einstein's time. People knew that there was lots of other stars, and they called those stars their galaxy, the Milky Way, but they had no idea about anything else beyond it, so they assumed that that was it, and everything around it was for infinity, just empty space. So we were part of some little corner of a galaxy that was just there in empty space, what meaning can you make out of that? Well, there were some people, fortunately, that weren't quite as affected by this prejudice as Einstein was. In fact, Georges Lemaitre had a very interesting background, and that may have something to do with the fact that he was able to first hypothesize the Big Bang model. Georges Lemaitre was a Jesuit priest before he decided to get a PhD in astrophysics. So he had a doctorate in theology, and then he went on to get a doctorate in astrophysics and went to Harvard and MIT. But perhaps, we don't know for sure, but perhaps because he had that theological training, he was more open to the possibility of a beginning of our universe. And so he used Einstein's equations and he said, let me work them out and see what they are telling us. And pretty soon he discovered that if Einstein's equations, his original equations, not the ones that were modified, if Einstein's original equations were correct, then it means that a long time ago, all of the galaxies and the planets and everything were all together, because expansion implies that everything is moving away from each other, and if you put it all back together, then it implies that they were together a long time ago. So he came up with what at that time was called his primordial atom hypothesis. The idea of Big Bang was not even there. It was a name that was invented much later on. But it was basically the same idea. He said that in the beginning there was this explosion that happened from what he considered to be the primordial atom, and everything came out of that explosion. Einstein was not too happy with that. In fact, he said some pretty bad things to Georges. But Georges, he went on. He went on with his ideas, and luckily for him, in the same time that all of this stuff was going on, our telescopes were getting better, and we were starting to see things in our cosmos that we were not able to do before. And so, as I said, our sensitivities were developing to discover what was there waiting for us to discover. And so in 1924, Edwin Hubble made an incredible discovery first. He found out the Andromeda galaxy, which at that time was believed to be just one other fuzzy cloud in our Milky Way. As hundreds of other fuzzy clouds had been discovered, he found that it was not in the Milky Way. How did he do that? By figuring out a way of actually being able to measure the distance from the Earth to Andromeda. And to his amazement, he found out that Andromeda was 2 million light years away from us, and our galaxy was definitely not as big as that. And so this was an amazing discovery, first of all, because now suddenly our picture changed. We were no longer a galaxy floating in empty space and time. We were part of a collection of a large number of all kinds of different galaxies floating around in space. But that was still not a center. Yes, it was nice to have all these companions, but it didn't tell us that there was anything different, or that we could use this as to weave a story around. So to Hubble's credit, he made another discovery 4 years later, or 5 years later. He found out that these galaxies, and he was able to figure out a way with the help of other astronomers to figure out what the speeds of these galaxies were. And not only did he find out there were lots of galaxies out there, he found out they were all moving away from us. And to his, I guess credit, I would say, but it unfortunately sort of turned things the wrong way. He computed the age of the universe by looking at the galaxies and working backwards to see at what time they will be all together in one place. And he found out that the universe was 1.8 billion years old. Now, by then, geologists had figured out that the Earth was at least 3 billion years old. That didn't look good. The universe can't be younger than Earth, right? If the Earth came from it. So this was something that drew a lot of criticism. And as it is, people were biased against, wanting to have this kind of a universe that's changing and has an origin and all that. So a whole movement developed within the physics community to detract from this idea of a Big Bang. and to look at other ways in which this expansion could be explained. And it turns out there are many other ways that you can do that. Now here's a kind of a funny picture. This is Einstein looking through Hubble's telescope, and Hubble telling him, look, the universe is indeed expanding. And maybe you did make a mistake, even though you are such an amazing scientist. And to his credit, though, he admitted that he had made a mistake. He shouldn't have changed his equations, and he started to believe in an expanding universe from then on, but not too many others. The other people in the physics community wanted to keep believing that this could not be a way. And in 1948, a new theory was hatched by another physicist in Britain called the steady state cosmology, where he said, look, I admit the universe is expanding, but doesn't mean that the density of the universe is changing. So in other words, the universe might be growing bigger, but at the same time, it looks quite the same to us from eternity, which means that new galaxies emerge from in the middle between the other galaxies in order to keep the image of the universe that we get the same. And so that was a new hypothesis, and people who didn't want to believe in the Big Bang, they sort of, jumped onto the bandwagon, and they said, yeah, this is a decent explanation. There's nothing wrong with that. And for the longest time, the Big Bang theory was maligned. Nobody wanted to work on it. It was a kind of a dead end. There was no way to sort of figure out what was going on, even though Hubble's estimates did start to change. People discovered that there were some systematic mistakes in how he had calculated the age of the universe. And so the age of the universe had started to grow to about 5 billion years. So that was like not too bad. Maybe it's older than the Earth and so on. But yet the prejudice was so strong that not a whole lot of things would have happened until we get two people in Princeton to be bold and to say, hey, it's worth looking into this. It may be possible that we could actually do something to figure out whether the universe is expanding or not. And what they discovered, and it turned out that that was actually a rediscovery because another young Jewish immigrant scientist had about 10 years ago predicted that there would be a background radiation if the universe started in a Big Bang, but his ideas were ignored for all kinds of reasons. And nobody knew about it until Dickey and Peebles in Princeton decided that they were going to work on it. So Dickey told Peebles, who was a theorist, to do the calculation, and he did that. And he said, yes, there would be a radiation, and it would have this particular characteristic. And you can characterize radiation with a temperature. So he said that it would be 3 degrees above the absolute zero. We call that 3 degrees K for Kelvin. And then they said, let's launch on a program to figure out how we can detect that radiation. And so on the roof of one of the Princeton buildings, they started to build a replica of what the horn antenna is. It was a different kind of an equipment, but the idea was kind of similar. And then we know the other part of the story, and that is that actually accidentally Penzias and Wilson discovered the radiation before they could. And maybe I used the wrong word, because when Bob Wilson was talking about it, he said, boys, we have been scooped. I was trying to be a little polite. But it is the smoking gun. Because it turns out, and this is hard for me to explain without going into all sorts of deep physics, but the truth is that the characteristics of this radiation are such that there is really no way to explain it other than the fact that our universe started out as a hot, dense, small ball. We call it the fireball. That is the only way that such radiation could be present at this time in our universe. Okay, so now I'm going to tell you something about how this idea that you are now quite familiar with, how does this idea tell us that we are at the center of the universe, and how this idea starts to build back the possibility that we can derive meaning from a story that the universe is unraveling to us. So this is what it looks like. You know, if we are at the center, as that center galaxy, you might call it, the Milky Way, then all the other galaxies are moving away from us in all different directions, which kind of starts to tell us that there is something about us that puts us in the center. But this is more complicated than this picture tells you. And so now I'm going to use some props to help you understand how it's not just we who are at the center of this universe, it is every single point in our universe that has this concept of being at the center. So I should introduce her a little bit. Virender is also a professor in biology, and she's also my coach, because every time I give a talk, I rehearse it with her, and she gets me to the point where I feel more confident.
Thank you. He's being too kind.
No. So I'll have you blow a balloon just now. But first, this is what I use with my students, and I'm not sure how well you can really see this. It's kind of small, but maybe if I come here, you might see it better. Yeah. So this is kind of a poor man's way of understanding it, but it's a kind of a start. So this rubber band is a one-dimensional version of our universe. So if our universe was just a line instead of being this amazing space that we have, and if the galaxies were little paper clips that are hanging off of that line, then expansion would look like this, right? Now here's the thing. If you focus on the pink clip, let's say the pink clip is the Milky Way galaxy. If you just look at the pink clip, then you will see all the galaxies around it are going further and further away from the pink clip. Yeah, you see that? Yeah. Okay. All right, don't focus on the pink clip now. I want you to focus on the green clip.
Which is the green clip?
Oh, sorry. Yeah, this one here, I know the colors may not show up so well, but this one here, the third from my right hand. So focus on that. And as I stretch, notice that from that green clip, all the galaxies are also moving away, right? So it just depends on where you happen to be. If you were on that green galaxy, you would say that all the galaxies are moving away from me, and I'm at the center. And if you happen to be on the pink galaxy, you would have the same thing. So the nature of the expansion of the universe is such that every point in the universe can claim to be at the center. And that has to do with the fact that it's not the galaxies that are moving. That's what this gives a wrong picture. We think that galaxies are moving in space. Indeed, what is happening here is that the galaxies are staying in the same place, but the space between them is expanding, right? And if that is the case, then this will be true. Now, there is another analogy that people give, which, you know, I'm going to give you a lot of analogies today, and none of them are perfect analogies. They all have downsides to them because, after all, it's an analogy. And so this one, of course, is just one-dimensional, and this does make you think that things are moving in space. But the analogy that this tells you, I'm kind of losing my train of thought, the analogy that this tells you leaves out something very important, and that is that each galaxy stays in the same space. It doesn't really change. So that thing can be corrected a little bit if instead of this, we use a balloon. So of course, this is not a perfect analogy either. So when I use a balloon, basically what I'm saying to you is that instead of a one-dimensional universe, we have a two-dimensional universe, not a three-dimensional one, right? I'm using the third dimension to show what can happen to the universe. Actually, before I do that, I have to show you why we can represent the universe with a balloon. So let me just hold this for a second. Now, here's what Einstein discovered. So this was the incredible thing that Einstein told us. So before Einstein, two-dimensional space could be thought about in this way, flat, right? And of course, I can't do that here, but for people that were used to this, for them, it was extending to infinity in all directions. So that's what space felt like after Newton, right? Einstein said, no, that's not a good way to look at space. We have to look at space as something that can curve and warp and change. And when he wrote down his equations for the whole universe, what he found to his amazement was that space can curve and warp in such a way that it can fold on itself. And when space folds on itself, it becomes like a sphere. The only thing you have to understand here is that there is no inside to this sphere, because we are talking about 2 dimensions, and 2 dimensions can only be considered as the surface of this ball. And so in 2 dimensions, our space for Einstein would look something like this. It folds on itself. What that really means, for example, if you keep moving in this space, you will eventually end up where you started. In our space, if from Einstein's perspective, which we believe is the correct perspective right now, if I start walking along the direction of my nose, I will eventually arrive at where I am today, even though that will take me, I don't know how many trillion years because of how big the universe is. But that's what he discovered, that you can think about the universe as a ball, as a balloon kind of thing. So now let's talk about expansion. So here is our universe, thinking about it in this 2-dimensional way. So forget about the inside of the balloon. That doesn't belong to our universe. We're using the 3rd dimension simply to get our points across. And I'm going to ask Virender to blow this balloon. Now, these are galaxies on the balloon. They're meant to be kind of like spirals. And what you will see here is that if you focus on any of these galaxies, they don't change their position in terms of where they are on the balloon. It's the balloon rubber that is becoming bigger and bigger between them, and therefore they go further and further apart. So you start to get an idea about what it might be like when everything is at the center of whatever is expanding. So if you want to blow this balloon now as much as you can. And I didn't want to blow it because when I'm talking, my mouth is getting tired and I don't want to tire it anymore. So yeah, so there you go. That's good enough. So now, yeah, I'll call you later. But this, thank you. Thank you, Vrinder. So this is exactly a better analogy than the one that I just gave you, where you can now see that each galaxy didn't leave its place in terms of where it was on this whole surface. All that happened was that there was more rubber in between them, and that made everything go apart. And I can be on any galaxy that I want to, and I'll have the same experience. Right? There's one other analogy. I told you I'm going to give you lots of analogies, whichever one works better for you. Another one that is commonly given is a raisin bread analogy, where we assume that the raisins, and this is now a 3-dimensional one, so it has one advantage over this one, but it has a disadvantage that we think of ourselves as having a boundary, which we really don't, because a raisin bread does have a boundary. But as a raisin bread rises in the oven, what happens is that each raisin doesn't move. The raisin stays inside the same part of the bread that it always was. It's just that more bread comes in between the raisins, right? And so all the raisins seem to go further and further apart. And that's exactly what our universe is like, right? And therefore, it gives us a new paradigm. That's what's so important about this. And so far, we always thought about centrality as something that puts us in the center of space. Well, if I take a balloon or even this ball for something, it does not have any center at all, right? I mean, any point on this ball is equally symmetric in terms of the shape of the sphere than any other point. So if you think of the universe as just a ball, what happens is that all the centers go away. But now, if this ball is evolving, that means it's getting bigger and bigger. You get the idea of centrality, because now centrality doesn't come from space. Centrality also comes from the development in time. And this is why a time developmental universe gives us a central way to look at it that a non-time development universe can never do. So what is happening now is that from every point on this sphere, there is an unfolding going on. There is new space that is being created. That is evolution. But of course, you might say, well, what's the big deal about new space being created? Well, we also know that in this space, there is matter. And as this expands, that matter is getting more complexified. It is becoming stars. It is becoming galaxies, planets. And then on those planets, there's more complexification going on in terms of, organisms and so on and so forth. So at every point, in some sense, what we are now witnessing is an evolution of the universe, but an evolution of the universe from every center. And if the universe is evolving at every center, it is evolving through you, right? You are a center of this universe. And if you are a center of this universe, you have to ask the question, how is the universe evolving through me? Right? So this revelation is putting us face to face with a question that we otherwise might not think about. And that's what I want to leave you with right now. And I'm going to stop here. I mean, I have more to say about the other story, but I want to stop here because I want this to become more interactive. And I want everyone to have a little time to kind of talk a little bit about what does this mean to you, if anything at all. And then we can have a little bit of sharing, and we can have some Q&A after that, and then we can go on a little bit. Is that fine? So, of course, this is a quote from Brian Swim that basically talks about the centration that I talked about. So after 400 years of empirical inquiry, a great reversal has taken place, one that shows us to be at the center of a universe vastly huger than the solar system. We do not retain the cozy medieval geocentric world, but enter an immense evolutionary cosmos that is centered on its own expansion. The key word here is evolutionary. It's the evolutionary part that allows us to consider ourselves, in fact, everybody, and not even everybody, but every planet, every galaxy in the universe, to be at the center of the universe. And then here's a little tiny quote, which is so meaningful. Think of yourselves as the space that the universe has created in which to tell its story. That's exactly what's happening here. Yeah, isn't it? I love that quote as well. So this is the question I want you to think about. How does it feel to be one of the centers from which the universe is yearning, right? This is the new learning, the new knowledge that we have gathered. And think about the universe as yearning to unfold. That's what the universe has been doing all its 14 billion years. It wants to unfold from every point in space and for every complexification that it has created, and you're one of them. So I think what I would hope is that we can pair up. Whoever is sitting next to you, if three of you are kind of close together, you can do that. And I'll give 5 minutes to just think and share with each other what this might mean for you in your life. So what I would like to do is, if anybody wants to share something that emerged from them while they were discussing and talking, please feel free to say that to the rest of us, because we can all benefit from it. And also, if there is some big question that is weighing on you in terms of what I said, and you want to get some clarification on what it means, I can spend a little bit of time on it. I'm going to be very careful, though I can't, spend a whole lot of time on Q&A, but I want you to make sure that there's nothing really big in your head that you would like to get clarified. So yeah, please, anybody wants to raise their hand? Yes, Phil.
So I guess we homage to all the doers who I've met today, who are just amazing. I would say that it's for us to do the work, that we don't get ahead and accomplish stuff without figuring out our route and being doers. And I think that's the challenge.
Thank you. Yes, please go ahead.
This story is coincidentally in time happening at the same time as other stories, ecological stories. And there's a deeper learning by understanding biodiversity and climate change
Yeah.
To kind of right the ship and move us from the separation story to the we are all interconnected story.
Yes.
And welcome to the journey.
Yes. Thank you. Thank you. Thank you. Anybody else share or question that you have hanging in your head that you want to ask? Yes. Prior.
You can comment about the apparent complexity, the apparent arising of complexity from what seems to be simplicity. How is it we understand the evolution of the universe, but don't talk about the involution as much?
Ah.
How interiority comes into play.
Yes. Excellent question. I don't know whether I can do justice to it in a few minutes, but what I would say is that the story that we are told about our evolution is very much heavy with the idea of entropy, which is not what we really observe, because what we observe is complexification, and entropy would say that everything would decay over time to the. And so this is an aspect that I don't believe that science had spent enough attention and energy to investigate. There are new things that are happening right now. There is a whole theory of complexity and chaos that started about 50 years ago, and includes, for example, things like system theory that are finally beginning to understand why complexification takes place. And it's a whole another field. In fact, there is a word that's been coined by some people called syntropy. So the opposite of entropy is syntropy, and the universe has another aspect to it that allows things to come together to complexify. So I'll kind of leave it at that, but it's a very good question. Yeah.
What we are doing here today.
Good point. Yeah, we're coming together here and forming new stories in our heads and complexifying our community. Exactly, right. But that's what happens. Well, if there aren't any other questions, I'm eager to kind of move on as well. I'm going to present a few more ideas and then come back to some more Q&A. So I'm going to try and go through this here. Yeah, of course. This one? Yeah, sure. Yes, beautiful little quote. Okay. So now I'm going to touch upon the fact that not only are we at the center of the universe and the universe is unfolding through each one of us, but the story that has been unraveled by the horn antenna is a story that the universe has made available to us as a way for us to get inspired. So centration is certainly one thing, and knowing that you are at the center empowers us. It makes us think that we have a responsibility to the universe to do something. And someone mentioned there the ecological ideas, which shows how neglectful we are in terms of taking care of what has been given to us to continue to evolve. But also there is a message that comes from the possibilities that the universe is making available to us. In other words, we are not on our own, right? We have guidance, and that guidance is something that we need to tap into to make it possible for us to do the things that right now might think impossible. I mean, we're looking at our world today, and we're saying, how can we make a difference? What can we do to change the arc in which our universe is headed? And certainly being an activist is an important thing, and there's a lot of value in it, but it's also important to stop and listen to whatever guidance might be there for us that the universe has, and to capitalize on that guidance. So I'm going to tell you how potent the radiation is that the horn antenna actually gave us. It has incredible amount of information in it. It's not just light. People call it the afterglow of the Big Bang. It is much, much more than that. So first of all, here is one way of looking at our universe. It's yet another analogy. It has value in it, but they're not everything that this analogy helps us with. For example, this analogy is very helpful if you want to think about the time dimension. The time dimension in this analogy, by the way, the idea here is that we have a universe that started with a Big Bang, and then slowly the evolution took place, and we got planets, galaxies, and finally human beings, and all of that stuff. So this tells us, the time dimension, but it doesn't help us understand our centrality as much, because it sort of tends, the vertical dimension here is space, and the horizontal dimension is time. But in the vertical dimension, it makes us think that the Big Bang only happened in one place. And it did not. It happened everywhere, and that's what we're going to. So first of all, how does this story get coded into the photons that the Horn antenna detected? So we believe that our universe actually started out as a bunch of quantum fluctuations. So we believe now that our universe has a quantum origin. And what I'm showing you here is an animation of what it looks like if you go to the smallest length scales. Our universe is not stationary, it's not steady that you might think. It is a bubbling froth. It is full of dynamism, it is full of activism that you can detect at that level. And it becomes much easier to understand how something that is so active is bound to evolve. It's not going to stay where it is. And so what happened is that during this bubbling fluctuation process, there was some kind of a phase transition, and I'm just going to call it that because it's a physics term, very hard to explain, but so a phase transition happened, and we got something that we now call inflation. Inflation is an event that we have now begun to understand, which tells us that a very, very tiny speck of a universe that we had at one time, smaller than an atom, in which everything was densely compacted, suddenly became much larger. In fact, what they say is trillion times larger, and it happened in a trillionth of a second. That's what inflation is. And today, we call this inflation the Big Bang. So we now understand, in a way, where the Big Bang came from. That doesn't mean that we understand the whole mystery of the universe, of course. I'm not saying that at all, because there's plenty to also question in terms of, where did the quantum fluctuations come from and so on. But the inflation happened, and during inflation, a whole lot of matter and light were created. The light that was created at that time is the same light that we detect in the Horn antenna. But for a period of 380,000 years after the Big Bang, that light could not go anywhere. It was stuck in a tiny little it was trapped. Why was it trapped? Because all of the particles in that universe were charged, and that is electrically charged. Light is an electromagnetic radiation. It interacts with charge, and it gets scattered and reflected from charge, and it can't go anywhere. So our universe was opaque. It was pitch dark in our universe. In fact, in cosmological lingo, that is called the dark age of the universe. But it lasted for this much time, and then there was light. And that happened when the charged particles came together to form atoms. Atoms are neutral. They don't stop light, and suddenly the universe was transparent, and there was light everywhere. This light was visible light. This light, if we were there at that time, we would have seen, but over time, this light actually expanded, because of the expansion of the space, this light became stretched out more and more, and it turned into microwave radiation, because microwaves are nothing other than visible light stretched out. That's, it has a bigger wavelength. That's all that the difference is. And so this is what was detected. And, here's another balloon analogy. And in fact, if I didn't show it, but the balloon that Virender blew up didn't just have galaxies, it had little squiggles on it. And those squiggles represent the radiations. You can see the expansion of the universe basically makes the peaks of that radiation go further and further apart, which is exactly what wavelength is. So all of this stuff is coded in that radiation. And I'll tell you exactly what we have learned from this radiation. But now let me tell you how we slowly unraveled those photons in more and more accurate ways. So the very first map that we were able to make of the radiation was a map that told us that the radiation was completely uniform. So if you remember, the Horn antenna, the reason that they knew that this was something coming from the universe was because every direction in which the Horn antenna turned, they got the same radiation. And so the map is a uniform map, nothing very special, just a solid colored map that shows that it looks exactly the same in all directions. But then we sent satellites up into the air and got better and better maps of this radiation, and we started to find out that it was not uniform, that it had lots of heterogeneity to it. And this heterogeneity is what has allowed us to unravel large parts of our story. We have made this heterogeneity become more and more accurate. You can see that the Kobe map, sort of gave us a vague idea. The W map gave us a better idea than that. And the last one that we now have is called the Planck map, which shows you the accuracy with which this radiation is. This, folks, is the picture of our baby universe. So this is all that we have learned from this radiation. Now, I can't explain to you all the physics as to how we uncovered it. From this radiation, we were able to, first of all, tell, and that was the big discovery, that our universe started out as a hot, dense plasma of particles. We also were able to tell from this radiation that our universe had a quantum origin, because that speckledness that you see, we can actually draw graphs from that speckledness, and those graphs correspond to exactly the kind of randomness that we know exists in quantum fluctuations. So we know that our universe came from a quantum origin. That map also tells us those areas in the universe that had higher density than others, and without that you cannot have galaxies, because you need seeds on which galaxies can glom into. If you have a completely uniform universe, you would never ever have a galaxy. It will just stay the way it is all through its age. From those photons, we have been able to figure out the expansion rate of the universe. In fact, Brian Stone loves to tell us that the expansion rate of the universe is so sensitive to the possibility that it creates in the future. If the expansion rate of the universe was a millionth slower than it is, then we would have a universe that cannot form galaxies, because it would rip apart very quickly. If we had a universe that was a millionth faster in expansion than it is, it would have collected together too quickly into a black hole and nothing would have happened. Think about that. Just think about that the precision with which that expansion had to happen was just balanced on a needle, and that needle is the only possibility that enables life to come. Because without galaxies, you don't have life. Without planets, you don't have life. So to me, that one fact makes you really think about what's going on here. The radiation also tells us a lot about dark matter. Dark matter is absolutely critical to the evolution of our universe. Without the scaffolding that it creates, the ordinary matter would not have been able to form galaxies. In fact, it also tells us about dark energy, because during the time that the expansion was taking place, the dark energy changes the rate of expansion in a certain way. We can read that changing rate of expansion in the photons that we collect from the Horn antenna or its equivalent, and we are able to make conclusions about dark energy. And finally, it tells us about how much our space is curved, which allows us to figure out what the shape of the universe is. So this is incredible. I mean, the amount of information that is enclosed in those photons. To me, it looks as if, the universe wrote its story and put it in a bottle and then put it into the ocean, hoping that one day a boat would come by with humans in it and discover it. I mean, this is literally how you feel when you understand the science that's behind it. So it's really amazing. I mean, it makes you feel that there is guidance here, that we are not alone, that there's something happening. And in fact, there is other ways in which we are at the center of the universe. This is what the Horn antenna has told us. When we look in all directions, we get that radiation from all directions. What does that mean? That means our origin is there in all directions. It's not in one place. That first picture that I showed you, again, it's a very important way to look at the universe, but it doesn't give us that feeling that we get now from the Horn antenna, that we are surrounded by our origin. We are embraced by it. We are wrapped in it. We are being bathed in the message that the universe has sent us from that origin. And by unraveling that message, we can get guidance. To me, that's a very powerful thing. And here we come to this wonderful picture that I have, thanks to Karen for bringing it all the way from Denver so that I can show it to you. I mean, here it is, but here's a real thing as well. I guess maybe this is a better one because you can actually see it bigger on the screen. But this is a way of looking at the universe. Another analogy, right? But one that highlights what I'm talking about. And that is that we are surrounded by the fire of the fireball, and we are right here in the center. And then what is happening is that the universe is evolving from this fireball towards its center. And as it evolves, it forms galaxies, it forms planets, it forms life, and eventually we get to this place. This is an incredible, incredible image to keep in your mind. This is, to me, phenomenal, just to sort of think about what this is implying. And it's kind of hard to understand how this can be, that the universe has a place from which it originated, and yet that place of origin is something that surrounds us. It's not something that is, at some place a certain distance away from us. It is something that puts us once again in the center. So I'm pretty much getting to the end of this so that we can have some more discussion. Here is an image that kind of helps us understand how this can possibly be. And once again, it's an analogy, it's a little hard to understand. So once again, we have a balloon as our universe. So you're used to that now. In that balloon, let me explain this a little bit. This tiny balloon is the fireball. So this is the point in our universe when light was released from that fireball. By the way, at this point in its evolution, the universe was as hot as the surface of the sun. Of course, earlier on, it was way much hotter than that, millions and millions of degrees. But it was still a hot fireball at that point, and that's when light was released. So light is released from all parts of the universe, and it goes in all different directions. But those photons that come to us all have to be ones that are 14 billion light years away from us, because that is how long it takes for that photon to reach us since the fireball started. So the line from which all of the photons arose that made it to us has to be a circle on this sphere that has us as its center, because that way all of these photons from this line will eventually 14 billion years ago arrive at us, and we'd be waiting with our horn antenna to receive it. And that's exactly what happened. But now how did that become possible? It became possible because as the universe evolves, and I'm just arbitrarily putting 10 million, 100 million years, it was evolving much, much faster in the beginning. It has slowed down very much. In fact, in the beginning, the expansion rate was faster than the speed of light. And so these photons were not really getting much closer to us because the universe itself was creating so much space that they only had a little bit of advancement from where they started. But as the universe started to slow down, these photons started to get closer and closer to us. And as we go on further and further here, they eventually got us here, and this is where our horn antenna detected them. So now from this picture, you can see that what we are looking at is indeed this image. It's not the image that is here, because that's long gone. This was the past, right? When it started from here, our universe was not so big. Our universe was, in fact, a fireball. And therefore, what we are looking at now that is collected in the horn antenna is what originated from the fireball, because when this started, the universe was as small that it was just a fireball. So what we're looking at when we look around us, the horn antenna shows us, is in fact the edge of that fireball. Okay, done. So this is the last slide. Perfect timing, right? Jennifer tells me 1 minute and we're done. This is another wonderful little quote from Brian Swain. What we have discovered is an omnicentric evolutionary universe, a developing reality which from the beginning is centered upon itself at each place of its existence. In this universe of ours, to be in existence is to be at the cosmic center of the complexifying whole. A pretty similar message to what we had before. Another little quote is here: we exist then at the origin point of the universe, because every place in the universe is that place where the universe flared forth in its existence. Keep in mind, if I go back to this slide here, that this place where we are today, this is where we are today. That place hasn't changed. That place was here when the fireball was created. So where we are sitting today is the same place from which that fireball arose. So we today are in that same origin, that same place from which the fireball arose. We are, in that sense, at the origin of the universe, even right now. Right? This is the incredible thing. We're in the same place. Of course, things have evolved, but that's the place that we're in. So the last question that I leave you with, and if you don't have the time to discuss this, that's fine. We can just keep this in our mind. And that question is, how does the cosmic evolution story boost your confidence? Because that's what we all need, is we need confidence in having this journey continue through us. And that's a question to think about for you. Do you want some Q&A or leave it to later? Up to you. That's, yeah.
Let's leave it till later. But
Yeah, that's fine.
first, let's just give a round of applause.
Thank you. Thank you.
Just unbelievable.
Thank you.
Thank you so much.
Thank you.
I feel like we need